sequences. Write down the next two terms of each of the following sequence. Well, this is going down in 3, going down in 3, so on. It's a linear sequence that goes down in 3. So the next one would be going down in 3, minus 1, going down in 3 again would give us minus 4. Question 1b. This is a number that goes up in 1, goes up in 1, then goes up in 2, goes up in 3. Now to work out the next one, we need to spot a pattern in the second differences. Notice when you do 1 add 1, you get 2. And when you do 1 add 2, you get 3. So to get the next one, we need to do 2 add 3 to give us 5. So this would be add 5, and adding 5 to that would give us 13. Now to get the next one, after that, we need to add 3, add 5 to get what we need to add to this term, which is add 8. 3 plus 5 is add 8. Add 8 is 21. Okay, next one. Work out the first difference again, see if you spot a pattern. That's add 3, add 5, add 7. Looks like add 11, is it? Ooh, no, add 9. Again, look at the first difference. Add 3, add 5, add 7, add 9, and notice that they are odd numbers and they go up in 2. So the next one would be an add 11, because the next, so 3, 4, 5, 6, 7, 8, 9, 10, 11 would give us 39. Add 13 would give us 52. Bet you're waiting for the last question, 1D. Now 1D, just going to clear everything that's here, so pause the video if you'd like to make the notes. Okay. Question 1D. This is one of the most interesting questions out of the whole paper, in fact, because it tests your knowledge on whether you can see a fraction that could fit the sequence. Now, all of these fractions, 4 over 7, 5 over 8, 2 over 3, 7 over 10, you can try and work out what's going on. So this one's going up in 1, but then it's going down by 3, and then it goes up by 5. Over here, goes up in 1, down by 5, and up by 7. I can't see a pattern in any of these. You can try looking for a pattern with these 6 numbers, but it's very hard. What you could do, however, is manipulate the sequence. And you can try having different denominators. So if you change the denominator, make sure you change the numerator as well. But the actual key to this question is looking at this term. Now this term can be rewritten as 6 over 9. Give you a moment to think about that. Yep, times the denominator by 3 times the numerator by 3 to not change the fraction, and it gives you 6 over 9. So now rewrite your sequence again. 4 over 7, 5 over 8, 6 over 9, and 7 over 10. Can you see a pattern now? Well, clearly this is going up by 1, goes up by 1, and now it goes up by 1 as well. And the denominator goes up by 1, goes up by 1, goes up by 1 as well. So the next term, the fifth term, will be going up by 1, which is 8, and its denominator will go up by 1, which is 11. And the term after that goes up by 1 as well. 9 goes up by 1 over 12. Now with 9 over 12, we can simplify 9 over 12. Sorry, let me put the commas in. We can simplify that to 3 over 4. Now you'd ask yourself, why would you simplify this term? Because one of their terms is simplified, or the question's terms are simplified, we should simplify our term as well. So to finish off, you would write 8 over 11, 3 over 4. Put a comma, dot, 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 to show that the sequence carries on. Okay, question 2. Question 2 is asking us to calculate the first and 17th terms of the sequences. So question 2a, sorry. So the first term would define as n equals 1. So u1 is equal to 8 times 1, because our n is 1, minus 7. Now BIDMAS will tell us that's 8 minus 7, which equals 1. And when the 17th term, n equals 17, so u17, 17th term, is 8 times 17 minus 7. BIDMAS again, so multiplication first. 8 times 17 is 136. Subtract 7 gives us 129. Yeah, so the 17th term is 129. Now, 2b, I'm just going to rewrite un again, but this time it's going to be 2 times n squared minus 3 times n plus 3, just to simplify our working out. Now, when n equals 1 is our first term, so u1 is equal to 2 times 1 squared minus 3 times 1 plus 3. Now BIDMAS, I'm just going to write it down here, BIDMAS tells us to do brackets first, or no brackets, indices. 1 squared is 1, so we have 2 times 1, minus 3 times 1 plus 3. Division, no division, multiplication, 2 times 1 is 2, minus 3, 3 times 1 is 3, plus 3, and you are left with 2 minus 3 plus 3, which equals 2. So the first term of this sequence is 2, and the 17th term, u17, again is equal to 2 times 17 squared minus 3 times 17 plus 3. And indices, 17 squared is 289, so it's 2 times 289 minus 3 times 17 plus 3, and 2 times 289 is 578 minus 3 times 17 is 51 plus 3. Now, silly mistake number 1 made by a student in year 9 was they did 51 plus 3 is 54, then 578 take away 54. That is wrong. The sign in front of the term belongs to the term. So, this minus sign in front of 51 belongs to 51. So that is a minus 51. Now we have 578 minus 51, add 3, and if you put that into your calculator, 578 minus 51, add 3, you press the equal sign, you would get 530. So the 17th term is 530. And the first term is 2. Question 3. Determine the formula that generates 5, 22, 39, 56, 73. It's asking us to work out a formula. And when you've got a formula like this, you'd probably need your table. So if you don't draw your table, you probably won't get the answer correct. Now with this formula you can see it's increasing quite vastly, so it could be a quadratic formula or quadratic sequence. Let's check it out. Working out the first difference, I'm just going to write diff for difference, first difference. 22 take away 5 is 17. 39 take away 22. Whoops, 39 take away 72. Sorry, 22 is 17. Oh, okay, 17, 17. 56 take away 39 is 17. And 73 take away 56 is also 17. The first difference is always the same. So this is not a quadratic, it is a linear sequence. It is in the 17 times table, so it's 17n. Now we need to work out what the constant is that we need to add. So we need to go one term backwards. So it means we have to take away 17 because we're going up 17 if we go to the right. And 5 take away 17 is minus 12. So it's 17n minus 12, and that is our sequence, or the formula that generates this sequence. To finish off, to show you understanding, you would say UN, or the term sequence, is 17n minus 12. So we didn't even need this because it wasn't a quadratic, it was a linear. Question 4. Now this is most likely a linear. Let's take a look. 4a. First difference of this is 4. So first diff. And second diff is 6. Yep, so there is a change in the first difference, so this is probably a quadratic. The second difference is 8, so it's going up by 8. The third difference is 10. Check your steps for a quadratic. Tick off, calculate the first difference. Now the second difference it's gone up by 2, 2, 2. Calculate the second difference. The second difference is constant, so this is a quadratic. How many n's is our next step? Well, if you remember from the general formula of a quadratic and its sequence, we need to halve the second difference. So 2 divided by 2, which gives us 1. This implies Our sequence is 1n squared plus something 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 that we don't know yet. So our sequence in our table, step 3, is, I'm just going to leave it as n squared because much better than writing 1n squared. Now it's time to fill out the rest of the table. Well, the actual sequence is 3, 7, 13, 21, and 31. Our sequence is n squared, so n squared, when n equals 1, it's 1 squared, which is 1. N equals 2, it's 2 squared, which equals 4. N equals 3, and n is equal to 3. It's 3 squared, which is 9. This one would be 16 and 25. So we've done how many n's there are. Now the fifth step is the subtraction. We need to subtract the actual sequence from our sequence. And when we do that, 3 take away 1 is 2, 7 take away 4 is 3, 13 take away 9 is 4, 21 take away 16 is 5, 31 take away 25 is 6. So, if we were to add these numbers here to our sequence, we would get the actual sequence. Think about it again. 2 add 1 is 3. 3 add 4 is 7. 4 add 9 is 13. 5 add 16 is 21. 6 add 25 is 31. But these numbers change when n changes. So this must be a sequence itself. And the sequence is linear. It goes up in 1, so it's 1n. And the previous term is going back by 1, which is 1. So it's 1n plus 1. So if we were to add this sequence to our sequence, which is n squared, we would get the actual sequence. So our sequence, n squared, plus this sequence, which is plus 1n plus 1, would give us the actual sequence. And we can tidy this up a little bit. It's n squared, 1n is just n plus 1. So that is the sequence of the actual, formula of the actual sequence. Question 4b. Again, let's take a look and see what kind of sequence this is. Work out the first difference. First diff. And when we do this, this is 15, 7, no, 25. I don't know. Yeah, 25. 35 probably, so 79 take away 44, yeah, 35, and this is 45. So we've done the first difference. Now notice the first difference is different again each term, and it could be a quadratic. Let's check. So the second difference is 10, 10, and 10. Since the second difference is constant, it is a quadratic, and we can halve the second difference to give us 5n squared. So our sequence is 5n squared. Let's fill out the actual sequence, which is 4, 19, 44, 79, 124. So, when n is equal to 1, our sequence 5n squared takes this shape. So it's 5 times 1 squared. 1 squared is 1, times it by 5 is 5. When n is equal to 2, we have 5 times 2 squared. 2 squared is 4, times by 5 is 20. When n is equal to 3, 5 times 3 squared. 3 squared is 9, times by 5 is 45. And when n equals 4, 4 squared is 16. Just write it down. 4 squared is 16, times it by 5 is 80. And when n equals to 5, we get 5 times 5 squared, which is the same as saying 5 cubed. 5 cubed is 125. Forgot to check myself, so we've calculated the second difference. Turns out to be constant. We worked out how many n's there are. 5n squared. We've come to subtract now. When we subtract, 4 subtract 5 is minus 1. That is a really bad colour. Let me quickly change. Let's go for red again. 4 subtract 5 is minus 1. 19 subtract 20 is minus 1. 44 subtract 45 is minus 1. This one's also minus 1 and also minus 1. Notice that if we were to add this sequence to our sequence, we would get the actual sequence. Now, is this a sequence? Well, it is some sort of a sequence, but it repeats itself, and it's always minus 1. So if we had our sequence, which is 5n squared, and we added minus 1, or take away 1, we would get the actual sequence. So our sequence, which is 5n squared, take away 1 from each term, we would get the actual sequence. So why not just take away 1? So now un is equal to 5n squared minus 1. Check. N is equal to 3. 3 squared is 9, times by 4 is 45, take away 1 is 44. Is the third term 44? Yes. N is equal to 4. 4 squared is 16, times by 5 is 80, take away 1 is 79. Is the fourth term 79? Yes, it is. So our sequence is 5n squared minus 1. Now the last question is the second most interesting question. Question 5. What happens to the sequence un is equal to 2n plus 6 over 3n minus 1? I had very interesting answers. Answers such as this gets larger, the sequence becomes larger. A lot of you were trying to, well, not a lot of you, some of you were saying, through my experiment, n becomes bigger, and you only use 2 values. That is not an experiment. An experiment requires a lot more facts and a lot more proofs, a lot more work to actually say this is the case or this is a fact. To test this, try some values. Try n is equal to 100 or a 100th term. So u100, the 100th term, is 2 times 100 plus 6, so it's 206 all over 3 times 100 minus 1, which is 299. Put it now into your calculator, you would get 0.68896. Blah de blah de blah. Goes on. When n is equal to something bigger, let's check for the millionth term. When the millionth term is equal to 2 times a million, which is 2 million, plus 6 is 2 million and 6. Subtract over 3 times a million, subtract 1, which is 2,999,999. Putting this into your calculator, becomes What do you notice with these numbers? Now, try it for something even larger. And if you try something really, really large, for example, n is equal to 10 billion, then this number, the plus 6, won't matter, because then you have 20 billion and 6. 20 billion and 6, the 6 becomes negligible. So we're just left with 20 billion. And 3n minus 1 when n is a billion, 10 billion. This isn't 10 billion, sorry. Now it's 10 billion. Then we have 30 billion minus 1. This minus 1 becomes negligible. So all we're left with is un is equal to 2n over 3n. Can we simplify this? Well, n divided by n, just like fractions, so if I had 7, bad example, 14 over 49, this is the same as 2 times 7 over 7 times 7. We can cancel out the 7s to give us 2 over 7. In this case, we can cancel out the n's to just give us 2 over 3. And when you try n is 10 billion in your calculator, the number will tend to 2 over 3. So to finish off, you would say, as n becomes large, un, which equals to 2n plus 3 over 3n minus 1, tends to, it means goes near to 2 over 3. But it will never become 2 over 3. It will get closer and closer and closer and closer to 2 over 3, but it will never become 2 over 3. That's why we say tends to, and not equals to. If you write equals to, you will not get the mark. Hope it was useful. Make sure you write in red. Have a good weekend. Bye.